You guys remember, I can't remember if it was yesterday or before, where I reviewed a few things from pre-calculus. So in chapter 4, we start off really nice. And then we get into, it's not going to be difficult, there's just going to be a lot of steps to it about how to use calculus to help us improve graphs that we do by hand. So you did some graphing by hand in pre-calculus, hopefully, we reviewed the multiplicity stuff, which I was surprised that a lot of you guys had never really worked with that before, because it's an unbelievably useful tool. So we're gonna have all of that happening plus calculus stuff on top of that, right? And I'm not trying to make it sound horrible. It's not going to be a lot of work. It's just difficult work. It's just going to be kind of a long problem. So, as I promised, section 401 is not going to be hard. I don't know why I've got that up there now. Here. We can look at. Yeah, it's nice. Yeah, look at that. Ooh. We already did some of this before. Horizontal tangent lines. They're where the slope is 0, but they are where what might happen. What's happening on the graph for a slope of 0? What could be happening? We know this. In fact, this is how we sketch the curve. We start with horizontal tangent lines. And what's the most obvious place where the tangent line is horizontal? So can somebody sketch in the air a shape of something where the middle is a horizontal tangent line? Yes, okay, one like this. Isn't that going to be a horizontal tangent line? What would this also be? That would be the minimum, right? The lowest point. And so if it was like this, it'd have a horizontal tangent line at the top, and that's the location of the maximum point. In fact, to be more specific, it's a local max and a local min. So, for example, if I draw in my usual crappy style, oh, poor Jeff, poor everybody else. It doesn't really matter, the specifics here. How many local mins do you see up there? 2. There's a local min here. Kind of looks like it's there, man. And there's a local min here. We'll say it's right. There's a local minimums, right? And there's a local max. Where? Yeah, there's a local max here. Now, let me make this a little more extreme here. Yeah. Do you see how the domain is cut? It only exists between this and this, right? There's endpoints to this. So there's local mins. And you see what local mins means is there's a neighborhood around it where that value is the lowest value. Is that cool? So that happens here also. I love that that's the actual math term, the neighborhood around it. It's not just Jeff, you never know. And then here, same idea. So there's a neighborhood around that where that's the highest value, highest output. So pretty cool. And then there's an absolute max. Where's the absolute max of this occur? What's your gut tell you? Especially now that I read through it. So is this the absolute max? Oh hell, that's the absolute max. I like it. Now, if I let this be a smooth, continuous function and I did not restrict the endpoints, the maxes and mins have to occur at a place where what is true? Where are these occurring? What's true at where these are occurring? Yeah, this is a slope of 0. These are horizontal tangent lines. Cool. Now, obviously, this has nothing to do with horizontal tangent line. It just happens to be where it just stopped there. It didn't have a chance to keep going up or to turn around or whatever. I like it. So the nice thing is, let's start with absolute maxes and mins. And actually, let's start with the idea of critical points. Does a horizontal tangent line have to mean max or min? The most basic example is a cubish, right? A cube. What's it do right here? It's going to have Yeah, because if you take the derivative of x cubed, you get 3x squared. At 0 would have a 0 tangent line. But does it turn around? It goes, tricky. Right, keeps going up. So critical point, and let me see if you guys remember this. Does a max or a min have to occur where the horizontal tangent line, where there's a horizontal tangent line? Is there another way for there to be a local max or a min? Yes. And it's going to be the other extreme for the derivative. It's going to be something like this. Does anybody remember what the derivative at that point, how do we describe it? Undefined. It's not differentiable at that point. So the critical points is the collection of all x values where the slope is 0 or undefined. Does not exist somehow. Critical points, all x values where f prime of x equals 0 or f down there, or f prime of x does not exist or is undefined. Something freaky is happening there. That's the idea of critical points. So we find all the places where things could happen, and then we figure out if it really is happening. So we got to develop that test. We're going to test the critical points to see, are they true local maxes and mins, or are these little, are they something like this, the little tricksters? No, right? How we know so far? That's a beautiful idea. The idea of critical points. We're not going to stop saying that word for a long time. Right? That phrase, if you want to get all technical. So, for example, we've done stuff like this. Right? If I said find all the critical points, go ahead and do that. Find all the critical points for that function. Not too bad. The mistake that a lot of people made was they didn't factor this. They just started trying to identify places. If it's not factored, you can't set things equal to 0. It doesn't make any sense. So what can I take out of this? What can I take out of these two terms? Is everybody cool with this, by the way? Did I do that right? Yes. I can take how many x plus 2s? 1. And how many x minus 1s? 2. You can give 2, right? You always take the smallest powers you see. That's what can come out of both. He's got 3, so he's definitely got 2. So I can take out x minus 1 squared. So what's left here would be 2x minus 2. You have one of these left. Is that cool? 2x minus 2 is up here. And you'll have one of these left for this guy. So I get 3x plus 6. So I get x plus 2, x minus 1 squared, 5x plus 4. So again, where did the 2x minus 2 come from? Because I'll have one of these left. Take that And 2 of those, that's gone. 2 of those are gone. So 2 times the 1 that's left is 2x minus 2. 3 times the 1x plus 2 that's left, 3x plus 6. So what are my 3 critical numbers here? Yeah, negative 2, 1, negative 4 over 5. Just setting each of those pieces equal to 0, right? So that's the idea of finding critical points. Let me give you one. Is everybody cool with that one? We've done that kind of problem so many times. Seems to be important. What about this function here? Ooh. What you got, Jeff? Sure. Ooh, I like that. Yeah, let's do that. Find the critical points for this function. First step there. So how do you do this guy's derivative? What rule is it going to entail? Chain rule. I like it. So the 1/3. Yeah, 1/3 comes down times this to the negative 2/3 times 2x. So let's kind of clean this up. So I get 2x on the top, and I get 3 x squared minus 4 to the 2/3. So where are critical points? Where the derivative is 0, or where it's undefined, or does not exist somehow. Maybe infinite or something. So where is it equal to 0? 0. X equals 0. And where is it undefined? 2 and negative 2. It's x squared minus 4, so you get 2, right? Plus or minus 2. All right, so let's build this up. So that's one thing by itself, just being able to find critical points, critical numbers, right? Now, how do you use those critical numbers? The first level, let's just do the easy one. Let's do the absolute max and min. Absolute max and min is the easy situation. You got a winner, and you got all these other losers. So you got the biggest and the smallest, and everybody else is a loser. I want to find the absolute biggest value and the absolute smallest value. So where could that happen? So normally it's going to give me a confined, so it might be a question where it's totally infinity, negative infinity to infinity, but normally going to confine it within an interval. So I need to check the critical points that are in that interval and the endpoints, just like that first graph I had up here. So, for example, for this function, if I want the absolute max and min, also known as the absolute extrema. Extrema is just a way to say max and min all at the same time in one word. The extremes, right? On let's say on the, what are you trying to say, Jeff? On the interval, oh, what you want, Jeff? I don't know, man. -3 to 1. I like it. So what are all the things I got to check? This is too beautiful to believe. All you got to do is plug a bunch of shit into the function and see who wins. For absolute max and min, it's that easy. So where could it occur? What are all the things I need to check? I got to check 0, because that's in there. So I got to see what f of 0 is. I got to check what other critical point's in there. -2. 2 doesn't get a shot because he's not in there. He didn't meet the entrance requirements, so he can't win. And what else do I have to check? -3 and 1. And then I just step back and see who's the biggest, who's the smallest. So when they ask for absolute max and min, find the critical points and then check those along with the endpoints if they're in the interval.
Are we putting it into the derivative or to the...
You tell me.
Or to the...
If I put these into the derivative, it's going to come out to be 0. I want to know the absolute maximum value. So this is where we're starting to get into the realm of you're going to be taking derivatives and second derivatives, and you better use the right thing at the right time. I don't care about the slopes at these points. In fact, a couple of them are places where it's 0 or infinite, undefined. So I want to plug these into F. I want to see where the biggest output and the smallest output is. And I can see who's the absolute maximum, who's the absolute minimum. So you just got to plug shit in. What's f of 0? No. What's f of 0? When you plug a 0 in, what do you get? The cube root of -4, which is fine. I see some of you guys cringing. Is it pretty? No. Is it real? Yes. It's a cube root. So it's a cube root of -4, which is whatever the hell it is. Maybe somebody can put that in the calculator. -1.58, blah, blah, blah. Okay. What about f of -2? Well, that's going to be 0. That happens to be 0. I like it. F of -3, that'd be 9 minus 4 is the cube root of 5, which we can plug in the old calculator. It's definitely bigger than anything so far, right? Who is it? 1.7? Blah, blah. And f of 1 with the cube root of -3. So he's definitely not the smallest, and he's certainly not the biggest because he's negative. There's something bigger and smaller than him, so this one is going to be the absolute min. And this one is going to be absolute max. How do you guys feel about that? That's really kind of beautiful. You already know about finding horizontal tangent line locations. We've done that. Now you just got to add also finding out where they're undefined, or it does not exist somehow, right? Then you just got to throw them in the function, see which one wins. Okay, that's nice. Now, let's focus on local maximum. I'm going to use the same function, now we're going to talk about local maximum. What we normally do instead of plugging stuff in, because if I plug stuff in, do you see how that max is less than this min, for example? So you can't just plug shit in to figure out local max and min, because you could have a max that's lower than another min. Do you guys understand that? I can't do that. Here it works beautifully because I really just want the absolute biggest and the absolute smallest. Bam. Here, local max could be lower than a local min. So I can't do it the same way. So what the shit? What's the main difference between, in a calculus sense, between this and this? I don't know, Jeff, man. Right at the thing, it's 0. They're both 0 right at the point. Leading up to this point, though, what's the derivative? Leading up to that point, what's the derivative? Negative. Negative, and then it's positive. See how it changes sign? But it's going down and then up, meaning that must be a min. I know we can see that it's a min, but if you couldn't see the graph, if it's going down before and up after, that's a freaking min. Does that make complete sense? Of course it does. I don't care if you're shaking your head the wrong way. Here, it's going up to it and down from it. So of course it's a max. So what's the quickest way to see this is that number line thing that we've done before. So here, where are things 0 or undefined would be at 0, -2, and 2. So I'm going to put a z for 0 and 0 and an undefined there, just for myself. Just to remember what's going on. That's the slope, right? We're looking at the slope. That's what the slopes are doing at those points. Is that decent? All right. And again, you've got to keep in mind what it is I'm trying to figure out. I want to know, just like we said now, is it going down to this and up to it, or what? Is it going down to it and up from it? Then I know it's a minimum. It's going up to it and down. If it's going up and up on both sides, it's one of those little tricky things. I'm just resting. It's not going to be a max or a min. How are we doing so far? Yeah, I like it. So for this problem, it's the local max and min on the domain of this thing totally. It's not going to be a restricted interval. That's normally for absolute max and min. It's going to be a restricted interval. Okay. So, how do I do this? Well, I can just start plugging stuff in to these regions. Because the only place this thing can change sign is one of these places here. This is a nice continuous derivative, except on its domain. So it's going to be, it can only go through the x-axis where it's got a doorway where it could possibly change sign. So if I plug a 1 in, what's the sign of the answer? And what's really interesting to notice is this is squared, right? Do you guys see that? So this is going to be, if I plug a 1 in, it's positive over positive because that's squared. The bottom is going to be positive always. You guys see that? Why? Because isn't it being squared? It's the cube root and then squared. Okay, good. So the bottom is always positive. So when I plug a 1 in, I get a positive. When I plug a 3 in, positive. When I plug a -1 in, negative. When I plug a -18 billion in, negative. I just say that because I don't care about the number. It's just got to be in that region. And I don't care about the number output. I just care about the sign of the output. Now, where is there a true location of a max or a min, and what is it? Is this a max or a min? Why? It's going down and then down again. So it's going to look maybe like that, or I know -2 is freaky, but it's not going to be a max or a min. What about over here? It's going up and up, so 2 is not a max or a min. It's not going up to and then down from it. You guys, I'm hoping most of you guys are like, this can't be it. This is too easy, because it isn't hard. Some of you guys are like, no, I'm not saying anything like that at all. It's not that difficult. So what's happening at 0? It's a minimum. Why? Because it went down to it and up from it. So there's a min at 0, cube root of -4. Now that we sort of could have guessed. That's our absolute min, right? And it was the location, it was at a critical point. You can see our absolute max there, look, didn't happen at a critical point, did it? It happened at the end point. But you don't have to compare these at all. Very often they won't have a damn thing to do with each other, but in this case you can see. Now I'm really curious, why don't we try to graph this thing and see how it matches up with what we've seen. Let's graph this thing. Does the function itself have an issue at -2 or 2? At -2, it's 0. It's not a problem. Do you guys understand that? That's 0 happening. Who cares? That's just the output there. It crosses the x-axis there. Ooh, right? But obviously the slope is freaky there. So what probably happens, in fact, what is the slope at -2, for example? you have to do a limit as you go to negative 2. Isn't it going to be infinite? Aren't you going to get infinite slope there? Yes, Jeff. If you go to negative 2, from either direction, it's going to be negative over 0, which is negative infinity. It's going to have a negative infinity slope. So it's going to be going down, and then it's going to have an infinite, and then it's still going down. But what happens at 0? It bottoms out. Then it's going to go up. It's going to have an infinite slope at 2, and then it's going to go like that. So I bet you it's going to look something like this. I really am not certain, but that's a guess. So let's see what it looks like. Clear, 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 clear. Go away. Okay. So the cube root, so I'll just do x, where to go? X squared minus 4 to the, what was it? 1/3. There's a way to do a third root, but I just didn't feel like it. Let's zoom 6 this thing. Jihad, there it goes. Yeah, cool. I like it. And of course you guys are like, well, you've done this shit a lot. Well, yeah, but I'm trying to show you. I really, in going into this, I truly had no idea. This is not like a function I know. I'm not trying to show off or shit, but once you do this enough, you can get a really good sense. You can just sketch a really rough sketch, and it actually is pretty easy, right? Now, we're going to get even better. Once we learn, like, the second derivative and what that means, we can make an even better sketch. We'll have more information about what this thing looks like. Yes?
Why did you call it an infinite slope?
Oh, because if you try to plug a negative 2 in, don't you get you get negative 4 over
Yeah. But it
0.
doesn't matter that it's changing after that section.
It's not changing, though. It's going down. Right here, the tangent line is straight up and down. So it's got an infinite slope there. That's what that means. That's where you can have a function that's nice. And it looks like a nice function. Looks like, I want to get a beer with this function. But right here, at 2 and negative 2, the tangent line is infinite. Now, what could happen there is it could do one of those cuspy things, and then it would be a minimum. That's why the critical points include places where the derivative freaks out. Undefined or non-existent. Because it could do one of those cusp things. But here it didn't. It did one of these, no, I'm not gonna do this. I'm gonna just keep going. It wasn't a max or a min. And you don't have to know any of that shit to be able to get to this point right there. We can just see that right off of this. Again, remind me, how did we get those values? We plug stuff into what? The derivative, because I'm curious about the slope around these critical points, because that's what's going to tell me if it's a max or a min. Now, how did I get cube root of negative 4? I plugged 0 into the function itself, because then I wanted to know what the hell the point was. Where is this thing happening? That's what I meant by you better use the right function, the f or the f prime, or eventually the f double prime. You got to know what it is you're looking for right then. All right. So here, let me give you this. I'm talking way too much today. And you're like, yeah, it's normal. All right. Jeez.